Researchers uncover key clues about the solar system's history. This is by Lindsay Vilak, University of Rochester, on phys.org, in a new paper published in the journal Nature Communications, Earth and Environment. Researchers at University of Rochester were able to use magnetism to determine for the first time when carbonaceous chondrite asteroids, that is, asteroids that are rich in water and amino acids, first arrived in the inner solar system. The research provides data that helps inform scientists about the early origins of our solar system and why some planets, such as our Earth, became habitable and were able to sustain conditions conducive for life, while other planets, such as Mars, did not. The researchers also give scientists the data that can be applied to the discovery of new exoplanets. They said there is special interest in defining this history in reference to the huge number of exoplanet discoveries to deduce whether events might have been similar or different in exosolar systems. This is what John Tarduno, the William R. Keenan Jr. Professor in the Department of Earth and Environmental Sciences and Dean of Research for Art, Science, and Engineering at Rochester said. He said this is another component of the search for other habitable planets. Solving a paradox using a meteorite in Mexico. Some meteorites are pieces of debris from outer space objects such as asteroids. After breaking apart from their parent bodies, these pieces are able to survive passing through the atmosphere of our Earth and eventually hit the surface of our planet or moon. Now, studying the magnetization of meteorites can give researchers a better idea of when the objects formed and where they were located early in the solar system's history. Tarduno says we realized several years ago that we could use the magnetism of meteorites derived from asteroids to determine how far these meteorites were from the sun when their magnetic materials formed. In order to learn more about the origin of meteorites and their parent bodies, Tarduno and the researchers studied magnetic data collected from Allende meteorite, which fell to Earth and landed in Mexico in 1969. The Allende meteorite is the largest carbonaceous chondrite meteorite found on Earth, and it contains minerals, calcium, aluminum inclusions that are thought to be the first solids formed in the solar system. It's one of the most studied meteorites and was considered for decades to be the classic example of a meteorite from a primitive asteroid parent body. In order to determine when the objects formed and where they were located, the researchers first had to address a paradox about meteorites that was confounding the scientific community, and how did the meteorites gain magnetization? Recently, a controversy rose when some researchers proposed the carbonaceous chondrite meteorites like the Allende had been magnetized by a core dynamo like that of our Earth. Earth is known as a differentiated body because it has a crust, mantle, and a core that are separated by composition and density. Early in their history, planetary bodies can get enough heat so that there is widespread melting and the dense material, which is iron, sinks to the center. New experiments by Rochester graduate student Tim O'Brien, the first author of the paper, found that magnetic signals interpreted by prior researchers was not actually from a core. Instead, O'Brien found the magnetism is a property of Aldente's unusual magnetic minerals. Determining Jupiter's role in asteroid migration. Having solved this paradox, O'Brien was able to identify meteorites with other minerals that could faithfully record early solar system magnetizations. Tarduno's magnetic groups that then combined this work with theoretical work from Eric Blackman, professor of physics and astronomy, and computer simulations led by graduate student Atma Anand and Jonathan Carroll Nellenbeck, a computational scientist at Rochester's Laboratory for Laser Energetics. These simulations showed that solar winds draped around early solar system bodies, and that it was this solar wind that magnetized the bodies. Using these simulations and data, the researchers determined that the parent asteroids from which carbonaceous chondrite meteorites broke off arrived in the asteroid belt from the outer solar system about 4.56 billion years ago, and within the first 5 million years of the solar system history. Tarduno says the analysis and modeling offers more support for the so-called grand tack theory of the motion of Jupiter. While scientists once thought planets and other planetary bodies formed from dust and gas in an orderly distance from the Sun, today scientists realize that the gravitational forces associated with giant planets such as Jupiter and Saturn can drive the formation and migration of planetary bodies and asteroids. The grand tack theory suggests that asteroids were separated by the gravitational forces of the giant planet Jupiter, whose subsequent migration then mixed the two asteroid groups. And he says, this early motion of carbonaceous chondrite asteroids sets the stage for further scattering of water-rich bodies, potentially to Earth, later in the development of the solar system, and it may be a pattern common to exoplanet systems. Water-rich bodies, we're talking about comets, which have ice. So that's amazing. This is by University of Rochester on phys.org. Please leave your comments. Thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.